My guest today is Rodney McInnis.
My favorite subject in high school was physics. I went on to do a Bachelor of Science in Physics and then did my graduate work and received a Master's of Applied Science in Electrical Engineering, where my research was in semiconductor physics. I presented that research at the International Modeling and Simulation Conference back in Pittsburg in the late 80s. I've worked in industry ever since. The interview today is the Climate Bell debut, explaining my understanding of the physics and modeling of the greenhouse gas effect on climate change, as well as the results I feel will be appreciated by many. I just want to thank you, Tom, for the invitation to debut on your channel, yours being one of the great YouTube channels on this topic, so thank you very much. I'm going to be presenting a novel engineering approach to precision and accuracy in computing the greenhouse gas effect on Earth's temperature. By engineering approach, I mean a methodical assembly of the necessary set of components to solve the problem and solve it now. Those components have been integrated into a tool anybody can access. The problems around climate change seem to be an escalating set of severe, costly, and restrictive mitigation actions underway to curb greenhouse gases. These are being implemented by governments and non-governmental organizations based on reports coming out of organizations such as the IPCC. Their guidance has wide-ranging temperature predictions from rising greenhouse gases for this century, values they say will be dangerously high. From my point, their lack of precision and their shifting estimates suggest their science and their computational models are poor. Climate Bell was created early on when preliminary calculations I did revealed that the general narrative on climate change was significantly overstated. It was created then in hopes of fixing any errors in the science and so contributing to defending the security and affordability of transportation freedom, food, and energy, all of which are critically important to humanity. I like Richard Feynman's spin on science. Science is the belief in the ignorance of experts. GHG Lab is available to any individual or organization that wants to join in that defense by showing an accurate computation for the effect of rising GHGs. It not only does the computational work, with its plots and easy click adjustments, it is a great teaching tool, and I think many will find it educational and fun to use. This is a screenshot of that tool. I call it a lab because you can go in and do any what-if GHG experiments you want. It runs the actual detailed physics calculations using the Earth system model, and the results are produced in about 5 seconds. I learned from my science fair days that a demo that can be played with and scrutinized at the fair was far more powerful than papers stuck to a poster board about something claimed to have happened elsewhere. GHG Lab looks complicated on its home view, but is easy enough to use even for an elementary child, as will be shown when I demo it. GHG Lab is a bit of a game changer in that a user no longer needs any climate change gurus to make temperature change predictions for any change in GHG levels. So my views on climate change have shifted over the last 25 years, from believing the proponents had good faith scientists understanding it, to becoming skeptical perhaps about a dozen years ago, to becoming annoyed with alarmism and the diversions of vast resources in the last few years. Those now threatening freedom, food, and energy, leveraging alarmism, doesn't sit well with me, to put it mildly. My inspiration for starting this was a video a friend sent to me in 2022 of Carl Sagan presenting to Congress in 1985. My friend and I disagreed on climate change back then. I quoted a few lines from Sagan's talk here, but essentially he assures Congress that greenhouse gas effects are well understood and claims they can be calculated accurately. I've provided the YouTube channel link for the long version of this session, where Al Gore speaks first, then Sagan, and a few other scientists. Having a physics degree, I saw doing a back-of-the-envelope calculation of temperature rise for GHG level rise as a personal challenge. I had to admit to myself I had a juvenile understanding of GHGs, and about all I understood was they absorb energy by vibrating, and through some mechanism I didn't understand at the time, they heat the Earth's atmosphere. I was also naive enough to believe that I could find a wealth of clear information on the web that would rapidly assist me in doing that exercise in a few days. I never realized at the time it would trap me in a drop everything else obsession. So this presentation is my current understanding of the greenhouse gas effect and how it warms the Earth. It has been a personal initiative of over 2 years of effort. The next 4 slides set up some scoping of the rest of the presentation. I'll also explain some tag icons that will be indicators of the nature of some points or slides. So I've got 2 groups in the audience today that I'm sharing with. Some have a relevant science background and others are non-scientists. And I want to make it this presentation worthwhile for both. For the scientists specifically, both academic and those in industries that are critically affected by the mandates, I'm looking for them to review my physics and modeling as soon as possible through an open peer review forum created for this purpose. So to expedite that, I'm explaining the 12 pieces of the puzzle I've assembled to solve the temperature calculation. But I'm going to make it as understandable and as interesting as best I can for lay people too by using non-technical analogies tagged NTAs in the presentation. I'm expecting that many will be interested to hear the 7 climate change industry flaws in the physics and modeling that became obvious through the R&D and using GHG Lab. These will be tagged as CCIF in the presentation. And to keep the presentation shorter but provide scientific information that I think should be included, I've tagged some slides, flash slides, where I'll just speak briefly about the content. And then any in the audience can go back and read the slide later on. There's just a few of those, but people might want to note down a slide number for revisiting later. A key part of the presentation is to show and explain the set of 12 pieces that allows one to accurately compute the temperature change for a change in GHG levels. I'll be showing GHG Lab experimental results and explaining the validation and accuracy of GHG Lab. There are dramatic differences between what the IPCC predicts and what GHG Lab computes. I'll be identifying 7 significant climate change industry flaws in physics and modeling. I'll be raising questions about our understanding of the greenhouse effect on Venus, and I'll be doing a quick demo. This has been a journey from effectively no understanding of greenhouse gases to creating GHG Lab, and some of my learning experience in the past I can credit to accelerating and guiding me. Serendipity also played a role a few times in this. So the word believing is something we say frequently in conversation, and it may carry the day in religion and it may carry the day in sports, but it is effectively an assumption when it comes to sorting out contentious scientific matters. Guessing a solution and then proving whether it's correct or not is a frequent approach in physics, as a pattern is seen in a problem that fits a solution method used for another problem solved in the past. However, for a multidimensional component-based approach, I think reason and understanding is the method to build a set of pieces that together can solve the problem as different pieces move into and sometimes are later rejected out of that set. And finally, knowing is believing with blinders on and hanging out with the settled science crowd, and that doesn't seem like much fun. So in terms of a first principles approach, after taking the personal challenge to try to calculate this and starting to search for understanding, I came to realize that there was a mess of information, and it was quite disappointing in terms of sorting out how exactly GHGs heat the atmosphere so I could do some calculations. So it became apparent that this would take more time than I thought. So I set out to do things from a first principles approach and build a set of valued pieces that seemed to be needed to do reasonably accurate temperature calculations. Each piece was qualified on fully satisfying the criteria of being A, an essential piece, B, a piece that is accurately quantified, C, conforming to a physically realistic model, D, having the right amount of detail to be useful, and finally, a piece that I actually understand well. And so now we start. This is an important slide to explain how Earth's temperature is controlled so people don't misunderstand what Climate Bell's focus is. On the left, I've listed several of the mechanisms or effects that influence Earth's global temperature average. Climate Bell is only focused on one of them, the effect of GHG levels on temperature. An easy non-technical analogy is to think of the Earth as a big warehouse. The warehouse is cooled or heated by a group of heat pumps, each representing a different effect as in the Earth system, each working independently and each having their own thermostat. Changes up and down on those separate thermostats have a combined effect and determine whether the building gets warmer or colder. And right here, off the bat, we can name 2 major climate change industry flaws in modeling. First, they pretend that CO2 rising is the only effect that can account for their claimed temperature rise during the Industrial Revolution to calibrate their equilibrium sensitivity number. Secondly, they have a temperature record that is suspect with questionable data adjustments and the nagging problem of ignoring the urbanization development over the last 100 years around many of the temperature monitoring stations. This is not my research, but that of others, of which have done a masterful job. The most prolific of one who does a masterclass job on both debunking the weather event claims and pointing out significant flaws in the temperature record in my mind is Tony Heller. So the GHG thermostat is one where human activity has an influence, and we need more accuracy than the IPCC produces to avoid needless mitigation policy mistakes ongoing and into the future. Over the last 20 years, as I see it, two camps have emerged regarding greenhouse gases and climate change. Camp 1 says there's no need to do anything about it, and Camp 2 says we need to take action. Camp 1A believes there is virtually zero effect or is totally saturated, and they have scoffing disbelief. Camp 1B acknowledges that there is an effect, but it's too small to create a noticeable effect over a lifetime. They dispute claims of worsening weather events and believe there is no climate emergency. Camp 2A believes there is a significant effect from rising GHGs, that the GHGs have caused noticeable warming and noticeable worsening weather events, and think we need to do some things to reduce GHGs, but fall short of claiming it's an emergency. And Camp 2B says it's a major effect. It will raise Earth's temperature many degrees a century. We're at the point of no return, right around the corner. We're going to cause mass extinctions, and we need to spend trillions to fight this emergency. Some in Camp 2B sound like they're in full-fledged Chicken Little, the sky is falling mode. So this is the first of 3 lessons in the presentation, and a lesson I learned almost 25 years ago. And it really taught me that simplicity to solve a problem sometimes lurks right in front of us if one reconsiders the approach to the problem. Solving physics problems is sometimes a matter of partitioning the problem for simplicity. I think it is worthwhile to describe this learning experience for a couple of reasons. The lesson I learned and I'm about to describe was instrumental in how I approach my R&D on climate. More importantly, it might encourage your audience when they see this to be open-minded in considering that there may be another approach. It will be my task to persuade them of a simpler approach to solving the problem that yields a conclusive result. So back in 2000, we were working on a compact computer server that used a newly announced processor, one that had the same performance of an Intel processor, yet consumed only 1/6 the power. We were studying a technical concern on our first prototypes and wanted to do a system power budget. We needed to know how much power the processor drew, but only had on-chip temperature monitoring. Measuring power wasn't possible, as described in point 1, but simulating, as described in point 2, would be possible. However, we were resource constrained. And here's a picture of the top of the board and a picture of the bottom of the board. Underneath the board, there's the memory, which gets quite hot, and it's right near the processor. And the processor is basically under that gold heatsink. Oops. We had decided to live without the knowledge of the processor power consumption. However, a couple of weeks later, the serendipitous choice in the heatsink gave me an idea to create a known thermal disturbance at the processor die to characterize the system. And this is how it was done. Shown here on the left is the actual processor, and it's a flip chip design. So the actual semiconductor back is right up at the top, and that presses against the heatsink. The opportunity was a slot in the particular heatsink choice where I could slide a power transistor in over the die and press it down with known quantities of heat injected. And we used 4 levels from 0.5 watts to 2 watts. And this is what it looks like graphically. And we fit a line to the points, and knowing room temperature at 0 power when the system's turned off, we solved for idling power and power at maximum compute load. And now using the on-chip temperature measurement and software, we knew the power anywhere in between. The takeaway lesson I never forgot was a complicated modeling problem was solved by realizing a simplicity and creating a new method. My approach to greenhouse gas modeling was to look for any such simplicities that could span complexity. In my set of 12 pieces, there were 4 simplicities found for the physics and modeling. These will be discussed in the next section on how to compute the greenhouse gas effect accurately for temperature change. As Einstein said, everything should be made as simple as possible, but not simpler. Now I'll begin to explain the puzzle pieces in hopes of persuading your audience it really works. By puzzle piece, I don't mean every one was a mystery. Some are just straightforward elements of solving the problem thoroughly and convincingly. The first puzzle piece needed was to find established data on Earth's atmosphere for average temperature, pressure, and density versus altitude. This was used to build a vertical model for calculations of absorption of infrared emitted energy from Earth's surface traveling up through the atmosphere. The data produced by NOAA, NASA, and the U.S. Air Force met that need, and a 16-layer model was created to solve the absorption by any greenhouse gas or mixture of greenhouse gases. In the equation shown, alpha is the absorption coefficient at a particular wavelength of infrared emission, and x is the thickness. The second piece of the puzzle needed, and the first of 4 simplification realizations, was the concept I called total scattering. Shown here is that 16-layer model that I just mentioned. As infrared light travels up through the atmosphere, in particular wavelength regions that align with the absorption of various greenhouse gases, the greenhouse gases absorb infrared energy, the photons, and convert it into vibrational energy of the greenhouse gas. Then they release the energy a brief time later as infrared energy, new photons. Because the gases are spinning and colliding, the direction of each release is a random direction, and hence the term scattering. When 99% or more of the photons get absorbed on the way up to outer space, I call that situation total scattering. Using the atmospheric model created for Earth, the absorption coefficient as measured in the previous equation was found to be 5.4 times 10 to the minus 4 meters to the minus 1 to achieve total scattering. And a non-technical analogy for total scattering can be considered when you drive at night in a thick fog. The opposite lane is completely dark because the light from an approaching car is being totally scattered by the fog. At some nearing distance, you make out faint headlights, and that is because the absorption is no longer sufficient to scatter the light completely. The third piece of the puzzle was finding the detailed absorption spectrums for each GHG. HYTRAN is a database that was started in the 1960s to provide molecular absorption and emission spectrums that could be shared by scientists around the world for many types of needs. I wasn't aware of it when I started my R&D, so I first went to research papers I could locate that led me in a computational direction of using average coefficients in the region of wavelengths. I thought at first this step function approach was reasonable, but later wasn't satisfied and found that published plots of various GHGs where I could digitize slopes of side bands and top of subbands to achieve more accuracy. Later, I thought, if only I can get the data that these plots are based on, I can load that into Microsoft Excel and write a little code to scan the data and do that digitization more accurately and automatically. In proceeding to do that, a week or two later, things changed when I realized this was a breakthrough. And instead of dealing with each greenhouse gas separately, I could build an integrated greenhouse gas coefficient spectrum out of all the greenhouse gases: carbon dioxide, methane, nitrous oxide, ozone, and water vapor. There are multiple places to find the HYTRAN data, but I highly recommend this one that I use because of how easy it makes things. And it's also a wonderful database tool for learning too. The fourth piece of the puzzle needed, and the second of 4 simplifications, will be shown in the next few slides. To start, these images show satellite observations of Earth. To the left is shown 2 views of the Earth, one showing reflected solar radiation and the other emitted infrared radiation. The elongated view on the right is also emitted infrared radiation with a total globe projection. They visually confirm the bulk of the infrared radiation is north and south of the equator, some 30 degrees or more, and is coming from the surface of the Earth predominantly. There are many diagrams one can find on the internet of Earth's energy budget. Most have similar features and numbers vary slightly. This diagram is from NASA. There was a movie I remember from over 20 years ago called Antitrust. It probably appealed to me since I'd already worked 15 years in telecom, and it was about a global communication satellite network, sort of what Elon Musk is doing currently. Anyhow, the pivotal line in the movie was memorable. The answer is not in the box, it's in the band. For over a year, I had an incorrect understanding about the next puzzle piece that I'll explain a few slides from now. When I finally figured this one out, the Earth system, I remembered that movie line and adapted it. The answer is in the box and in the bands to solving the greenhouse gas effect on temperature. And the box is the Earth system. The bands are the 5 GHGs integrated into one absorption spectrum. And the computation is how much blackbody infrared energy destined for outer space gets intercepted by GHGs and how much of the energy in that specific qualifying intercepted radiation eventually returns to space. There are 5 key rules within the Earth system for doing the calculation. The only source of the outer space-bound full-spectrum black-body radiation are Earth's surface and cloud tops. The only source of outbound resonant band radiation are greenhouse gases. Only the outer space-bound black-body radiation counts for the greenhouse effect. Greenhouse gas absorption captures that black-body space-bound radiation by the Earth system, and only greenhouse gas emission controls the release of some of that captured energy back into space. All other thermodynamic activity within the Earth system is irrelevant to computing the global greenhouse effect for the Earth. I'm going to illustrate what was just said in the previous slide regarding the black-body emission part of the infrared photons with a non-technical analogy of water pumps and pipes in the Earth system to help people better visualize. Pump 1 is the sun pumping water into the Earth system, the majority reaching the ground as W1, but some is captured in the atmosphere as W2. Pump 2 is the water leaving the Earth system from the ground as W3, but the pipe is tapped and some of the water stays in the Earth system as W5. This is analogous to the absorption part of the greenhouse effect. Pump 3 is water leaving the Earth system from the cloud tops as W4, but the pipe is tapped and some water stays in the Earth system as W6. This is also greenhouse gas absorption. Pump 4 is the water leaving the ground but is captured by the clouds and stays in the Earth system. None of it can get out, and so the tap in the pipe is irrelevant. Increasing the flow of W5 and W6 is like greenhouse gas levels rising and results in Pump 2 and Pump 3 needing to push more water to hold the equilibrium, which is Earth's temperature rising. A non-technical analogy may further the understanding as to why internal modeling of energy transfer isn't productive. Hiking calculators are used by the military and recreational hikers to maintain digestive energy throughout the hike so the slower fat-burning energy recruitment doesn't occur. The calculator inputs represent factors affecting the energy needed for the work done by the hiker. The calculator's output is how many calories need to be eaten. No internal processes are necessary to be modeled because most people operate at a similar 95% efficiency of converting food to usable energy. In the same situation with greenhouse gas effect, internal transformations mean nothing as no energy is gained or lost in these processes. It is only slightly more complicated in that the absorption is computed in the outer space-bound direction, and what is captured has a return efficiency defined in the next puzzle piece. Sorting the Earth system out in one's mind is a bit tricky, like looking at an optical illusion. Even when you know what the illusion is, it's hard not to see the illusion. Remember that the energy flows are simultaneous and not sequential. So when the Earth has an average surface temperature of 15 degrees Celsius and is radiating upwards, it is doing that in the presence of all the other energy transformations going on involving the Earth's surface, including a strong downward flux from GHGs. If one doesn't embrace this properly, it is easy to fall back into the trap of sequential energy transfer thinking within the Earth system. And also remember, the Earth doesn't heat itself. This is the 5th puzzle piece and involves the return efficiency of the absorbed outer space-bound infrared radiation. The first serendipity was that a few organizations, such as the Climate School cited on the left, mentioned that the 50% to outer space when mentioning the random direction of the emission from a vibrating greenhouse gas. However, my understanding was simplistic at that time, and I hadn't come to an understanding yet of the Earth system model previously explained. I quickly embraced it, believing that the 50% going to outer space being one direction and the Earth's surface absorbing it for the other. The latter was incorrect. The second serendipity was I didn't revisit that understanding for over a year, and before I did, was fortunate enough to get a convincing result from an early version of GHG Lab confirming that 50% was correct. Later, from the graphs of my earlier version of the GHG Lab and studying the NASA's Earth energy budget, I realized 50% going to Earth's surface was wrong in the random walk of photons being absorbed low in the atmosphere. My subsequent attempts at explaining the 50% by using the physics method of guessing a solution and proving it also failed. It was only after discovering it in the lecture notes of a professor who taught atmospheric physics course from the University of Wisconsin-Madison did I have my answer. And that was the third serendipity on the same puzzle piece. The sixth puzzle piece was to integrate the absorption coefficients into a single blend for the greenhouse gas levels for A and a single blend for the greenhouse gas levels for B. This was achieved extracting the high trend data for each GHG using the same detailed step interval so absorption coefficients could be added. Approximately 180,000 data points were extracted for each GHG between 3 microns and 20 microns. I then wrote a compression algorithm to shrink the data by a factor of 10, and calculation runs were done to ensure no accuracy was lost. Answers agreed between the full and compressed data sets using a 0.01 Celsius comparison precision. A blended coefficient table is simply the addition of individual coefficients that were scaled to their respective concentrations before being added. Once the blending puzzle piece is embraced, one quickly realizes 2 more major flaws in the climate change industry's physics and modeling. The climate change industry adds greenhouse gas radiative forcing values irrespective of band overlap. They should be dealing with detailed absorption spectrums and adding those instead. And worse, they claim that H2O is a strong greenhouse gas that amplifies CO2's effect, when in fact it is the opposite because of the overlap. Their mistake again goes back to not working with blending of detailed spectrums from high trend. A non-technical analogy may further help explain this problem. For the black-body infrared emissions of Earth's surface and cloud tops heading to space, the flow can be compared to fish swimming up a stream. A fish net downstream intercepting the fish first will lessen the effectiveness of a net upstream. The net downstream is like H2O absorbing infrared first before CO2. And if no fish get through the net upstream, that is like total scattering, as all are captured, either by the first net or need a bit more from the second net. The point is that the first net never amplifies the effectiveness of the second net. The seventh puzzle piece needed is graphing for observational checking of the combined absorption coefficients. The upper graph is the mixture of carbon dioxide, methane, and nitrous oxide. The lower graph adds ozone and water vapor. The black line is the absorption coefficient for Earth's atmosphere that achieves total scattering, 99% plus, as described in puzzle piece 2. Between 8 and 13.5 microns, you can see what is known as the atmospheric window, where some of Earth's energy escapes into space. Keep in mind that the y-axis is logarithmic, so going down the size of a y-axis tick from the black line results in only 37% of the radiation scattering, and 2 ticks down, it's less than 5%. Beyond 14 microns, the spectrum indicates total scattering and seems to be rising near the end at 20 microns. This leads into the next puzzle piece. The 8th puzzle piece needed, and the last simplification realization, was H2O completely takes care of the region between 20 microns and 100 microns and is in strong total scattering. Thus, as temperature of the Earth rises from rising GHG levels from the greenhouse effect computed in the 3 to 20 micron region, the greenhouse effect in the 20 to 100 micron region adds about a 10% rise on top of the other temperature rise. The 9th puzzle piece needed was to account for GHGs other than CO2 that weren't as well mixed between the surface of the Earth and the 50,000 meter modeling level. What was needed was the global average parts per million by volume values for each of the GHGs at the altitudes used in the vertical atmospheric model that was created at the beginning. This data was found in the atmospheric constituent profiles published in 1986. And there's the table there of the values that I used. The 10th puzzle piece needed to calculate the temperature rise by greenhouse gases for the rest of the century was to take a couple of decades of trend data and fit an experimental curve, exponential curve for each. Data from Statista.com was used, and the equations that were found are shown. They were checked for fit on the data, and CO2 was accurate to within 0.12%, CH4 0.39%, and N2O 0.07%. GHG Lab has a place to type in any year from 2030 to 2100 and get levels computed for input B automatically using those equations. In rewriting the equations, we can solve what year doubling happens for CO2, CH4, and N2O. It occurs for CO2 in 2141, for methane, CH4 in 2177, and 2247 for nitrous oxide. But the UN expects a population to peak later this century and then go into a multi-hundred-year decline. By year 2300, they say the median population estimate is going to be 7.5 billion, which is lower than today. So I think it's unlikely that we ever see doubling of any of the GHGs. The fifth flaw in the climate change industry is that they speculate on GHG levels throughout the rest of the century when they have a trend line to follow. By speculating and having some scatter points above the trend line, it only serves to get them meritless fear attention. The second learning experience I'm noting that accelerated my efforts has to do with my experience with Excel. About 15 years ago, I used Excel to write a simulator to solve a system of equations for a network of low-voltage LED lights. The contractors were doing custom designs of low-voltage LED lights outside of homes, driveways, backyards. Upon installation, issues including voltage drop could arise from long wire runs and the number and location of lights on those runs. The contractors needed a tool to simulate representative situations prior to install so they'd be confident they'd avoid a problem regarding current or voltage. So the takeaway lesson, even Excel 2007 had rich Visual Basic programming capability back then with math features to iteratively solve a system of equations. Also, the visual control of cells made it relatively easy to create an appealing graphical user interface. The lesson applied for Climate Bell after it was realized integrating the high trend data for the GHGs was part of solving the puzzle. It was obvious that a user-friendly tool was the way to go, and Excel would be a very efficient way to do it. So the 11th piece of the puzzle is to actually implement GHG Lab in Excel. And what I've done here in the slide, people can go back and look at it. I've identified various regions in the Home tab and some explanations. But there's more details found on the website linked by the GHG Lab Guide tab below. GHG Lab allows you to do almost any experiments with the 5 GHGs to see accurate temperature change calculations. And finally, the last lesson learned that I'm citing came from a digital semiconductor simulations. I worked in the research and design side of the telecom manufacturer back in the 80s, and they had their own semiconductor foundry. The time frame was the mid-80s, and the silicon chips back then were about 100,000 to 500,000 transistors. Some designs were failing due to timing errors that the simulator wasn't catching. The small consequence of a failure was a few months slip and perhaps $500,000 in cost. But the real big consequence was missing the buying decision of a big telecom carrier, and that could be hundreds of millions over a 10-plus year network build-out. I was assigned the task of figuring out what was wrong and fixing it. It became a 2-year project. My first thought was to check out the calculation models, but they were okay. Secondly, I checked out the simulator to see if it was implementing the models properly, and it was okay. So then I tackled the data behind the models and found multiple problems around centering. I also tightened the Silicon Foundry's process screening to guarantee holding a centered alignment with the corrected data in the models. So the takeaway lesson is always center a simulation with the goal of symmetric error bars. The lesson applied for Climate Bell, even though computational results were confirmed acceptably accurate without adding centering parameters, it was important to add the centering parameters to center each modeling aspect and also allow users to do a sensitivity analysis. The 12th and final piece then was adding fitting parameters and computing those centered values. So there's 8 fitting parameters that I added to GHG Lab. 5 of them are to make adjustments with respect to the well mixing of the gases. CO2 is well mixed. The other ones have deviations from holding a constant ppm going up through the atmosphere. And they haven't been hard-coded for the flexibility of allowing expert users to put in their own preferences if they have some differences, and they also can do their sensitivity analysis. There's three that are very esoteric. One is the path length fitting parameter. So the model was built on a direct vertical interception going up to space. But as you know, with the surface emission, it's a hemispherical even emission. And so there's a fitting parameter called path length fitting parameter to compute that. That's a bit esoteric. A more esoteric one is the cloud top fitting parameter, which compensates for the fact that we have some of the emissions coming off the Earth at an elevation. And so it means there's less greenhouse gases between that emission point and escaping the atmosphere. So it's like a deviation from assuming everything is from the Earth's surface. And the most esoteric one is the power retain thing, which is a slight deviation from the 50% factor I mentioned earlier. And that has to do with the Earth's curvature and the level at which in a particular part of the spectrum is the range where those photons launch from. So it's about Earth's curvature. So it'll be slightly less than 0.5, but not much. This is a flash slide. Should there be any interest in co-authoring one or more papers by some of those who peer-reviewed the climate belt physics and modeling, you can revisit the slide and perhaps reach out to me at some point in the months to come. This is a brief summary of how GHG Lab works. Input A is the reference point because we know what Earth's temperature and GHG levels are. So that's the baseline. Input B is where the changes are typically made. The high trend data has been compressed into nearly 18,000 fine slices between 3 and 20 microns. A and B each have their own integrated absorption coefficient column representing absorption coefficients in the slice for A and B. A and B each have their own power in the slice columns. The equation you see on the front of GHG Lab, the delta P equation on the GHG Lab, is the physics equation to compute the power in the slice. A and B each have their own absorbed power in the slice columns. The A and B absorbed in the slice columns are summed for a total power in each of A and B. Each sum represents the absorbed power, and 50% of that is retained, while 50% goes to outer space. For the absorbed power in the slice sums, if sum B is greater than sum A, the temperature of B will be higher, and if sum B is lower than sum A, the temperature of B will be lower. So then an iterative algorithm works the temperature of B until equilibrium is restored, basically doing the greenhouse gas effect in the calculator. Equilibrium is deemed restored when a comparison is made that differs by only 3 times 10 to the minus 6 watts per centimeter squared or less. The precision of the computation is down to 100th of a degree Celsius, and the accuracy of the convergence is 2 100ths of a degree Celsius, and can be verified with the manual adjustment controls for temperature B found near the Run button. This diagram shows the error bars in green growing the further away we are from the known values of the referenced year 2023. Besides the current values of the GHG levels and temperature at 2023, there is only one other place that we have some confidence in anywhere in this diagram, and we understand that place has a known temperature within plus or minus 3% for the GHG levels. That location is where all the GHG levels are set to 0 parts per million. This is the result that kept my confidence up that 50% to space was correct. The target was hit on the first shot with no fitting parameters needed, and before I'd realized I had misunderstood the physics behind the 50%. From the solar calculations that we've all seen, both camps pretty much agree that Earth would be between 33 and 35 degrees colder if it weren't for GHGs. So the target center being 34 degrees difference, plus or minus 1 degree, which is approximately plus or minus 3% error bar. The target was hit on the first computation of level B GHGs going to 0 and came out with 34.78 degrees. Whenever a completely different method in science gets the same result, that is mutually reassuring. I'm not sure if the climate change industry has ever produced this result in the opposite direction, perhaps not, given what I've seen so far. Considering accuracy, if the GHG effect was on the low side, say 33 degrees, the actual effect, and the calculator computed 35 degrees, or vice versa, that would be a 6% error. So to avoid needless debate, I've arbitrarily set the absolute accuracy of GHG Lab to a higher value of plus or minus 10%. So in summary, the GHG Lab calculation accuracy is plus or minus 0.02 degrees Celsius or plus or minus 10%, whichever is larger. The latest version of GHG Lab is 2.4, and on the left you can see default values still hitting the target, and the refined guesstimate values for the 3 esoteric FPs also hitting the target. I probably won't update the default values in the GHG Lab for the 3 esoteric FPs for many months. Even though they are slightly off-center, it isn't materially significant as they appear to be counterbalancing each other, and all the FPs don't have much sensitivity since our GHG levels are at about 80% total scatter from the infrared spectrum. Now let's look at some other interesting experimental results. Just to clarify, for GHG Lab, the copyright on the tool is referring to the software and the UI and not the use of unedited clipboard images. You can use all images from copy to clipboard freely without requesting permission, so long as they remain unedited. They can be used anywhere, for instance, emails, presentations, social media, content in a video, etc. Using those images is even appreciated as it helps to spread the word. So on the left, we see a doubling of CO2 in the presence of H2O has a 0.47 degrees rise. On the right, we see a doubling of CO2 with H2O removed produces a 0.80 Celsius rise. Both experiments include the other GHGs. This proves the problems the climate change industry have with their flawed treatment regarding H2O, as pointed out in the GHG blend puzzle piece. I've seen it written in papers that authors feel there are too many lines to process to work directly with high-trend data and need to go to the radiative forcing logarithmic approximations for GHGs. GHG Lab has no problem processing 2 tables of 5 GHGs using detailed line spectrums and computing an accurate result in 5 seconds on an 8-year-old laptop. Doubling methane, something that may never happen due to the UN's predicted population decline, but if they are wrong and it does happen, using the equation derived for this work based on the last 2 decades of trend data, it would occur around the year 2177 and would warm the Earth only 0.04 degrees Celsius. Doubling nitrous oxide, again, something that may never occur, but if it did occur, would occur around the year 2247 and would warm the Earth only 0.05 degrees Celsius. This should be enough to anger the agricultural industry. The water cycle on Earth is complex and not well understood from a modeling point of view by anyone. And I think both camps agree on that. However, it is generally viewed as being a negative resistance cycle, meaning it resists or pushes back against forces that might change the H2O ppmv. Therefore, when a temperature changes up or down, the final amount of relative humidity, RH, change is uncertain. The default mode of the calculator is to leave the ppmv of B the same as ppmv of A, and both are adjusted from the RH input field at the top that are currently showing 60. However, some may prefer to understand that the water cycle actually restores RH of B to that of A through evaporation. The uncertainty of how much, if any, H2O ppmv changes for a change in temperature is likely somewhere between the two. Equalized RH does a double pass, and that's a button on the thing, and basically it calculates the first temperature change and adjusts the RH to match A again. So it brings the RH up and then does a second pass. And that's what you see here, the comparison between, for all 3 GHGs doubling, it's 0.57. And when you equalize the RH, it's 0.65. Using the pre-industrial 1750 levels of GHGs, we see that there is a 0.27 difference due to GHG levels rising from then to the present. Therefore, the claims made by the climate change industry regarding 1 to 1.5 degrees are either caused by other temperature effects mentioned earlier in the presentation, or measurement error, or a combination of both. The detailed physics calculations show their assumptions are incorrect, and so their equilibrium climate sensitivity has significant error and no mitigation action should be taken using it. By the year 2075, using the trend data for the three GHGs, the greenhouse effect will contribute 0.21 Celsius influence on Earth's temperature. Other effects will combine to collectively influence whether Earth's temperature goes up or down. This is just an educational exercise to show how CO2 on its own is a powerful greenhouse gas in low concentrations, but becomes saturated as the concentrations increase. In going from 0 parts per million to just 10 parts per million, the temperature increases by 4.01 Celsius. The absorption spectrum relative to the total scatter line is shown, and the change in scattered power flux 2 is shown, and that explains the result. When 10 ppm is added to 421 ppm instead of added to 0 ppm, the temperature rise is only 0.03 Celsius instead of 4.01 Celsius. The change in scattered power flux between A and B is minuscule, explaining the resulting low relative temperature change. It should now appear clear that Camp 1B was correct. I think GHG Lab can serve as a catalyst for both camps to have a new dialogue. The conundrum of virtual stalemate between their experts has been broken. When I started this in 2022, I felt 1A and 2B are highly unlikely, but I was not entirely confident in picking a winner between 1B and 2A without computing results. With the 12 modeling pieces assembled and the results revealed, many will soon realize the virtual stalemate between both camps can now end quickly. And my feeling is that we should welcome early converts from Camp 2 with kindness, as they may be some of the most inspired people to redeem themselves through helping end the mandates and inspire more converts from Camp 2. Let's break from the presentation for a quick live demo, just to give you a feeling for the tool, and then we'll return to finish. We only have about 20% left, but they are interesting slides. All right, so we'll just do a few things in GHG Lab. You saw some of the results earlier. I won't go back and duplicate those results. But basically, GHG Lab over in this region here has a lot of quick preset buttons. And what they'll do is they'll input values for A and B, and they'll also work with what I call radio buttons here, which are select, deselect. So when you deselect something, it will actually go to 0, and you select it again, it comes back. The reason you're seeing a number here and a different number here has to do with the fitting parameters for the gas when it's not well mixed. So these have been figured out to adjust. So this is what's actually at the Earth's surface in terms of parts per million, and then it goes up through with the fitting parameter. Up here, you can set things like your average RH, the average Earth temperature. Over here, you can do things like type in a year 2050, and when you hit enter, the B values will change over here using those 3 exponential equations. It's nice to always go back at the end of an experiment and do reset all. It takes a few seconds because it's resetting the numbers, but it's also recalculating all the tables. And that makes sure that you haven't forgot something you've changed when you do your next experiment. So these buttons here allow you to quickly add double CO2 or double. You can always type in whatever number you want here, but saves you a lot of typing for some simple experiments. This one I put in for the farmers, the 4x So we talked about doubling happening, back or a couple hundred years. For quadrupling, just checking my notes here, the quadrupling of CH4 happens 316 years from now if the prediction of population collapse doesn't happen using that same curve. And for nitrous oxide, it's almost 450 years. So when I put that in here, we're going to see what happens when we quadruple. We leave CO2 the same, and then we hit run. And that's what all the fuss is about. 0.22 degrees Celsius if we quadruple the agricultural greenhouse gases. Now, I'm not calculating what the Earth's temperature is going to be because there's other things that factor into the Earth's temperature, but that's the actual greenhouse gas effect. I'm going to go back and reset that. And I'm going to go into doubling all 3, and I want to show people the curves. Curves are quite useful for educating. for seeing what's going on. And I'll just, okay, so it's reset. I'm doubling now all three of these GHGs. So A stays the same. And then I hit run. And get that 0.57 that we saw earlier. So here we've got so here I've got curves for the A absorption coefficient. That's the integrated spectrum. And then if you click on B, remember B was higher, you can see B. So I'm going to toggle back and forth. You can see the effect of doubling the GHGs in terms of what still is below the line. Everything above here is in total scatter. There's no additional effect. And you can also see over here the percentage that is in total scatter. So for A, it's 78.52%. And for B, it's 79.48%. So it's quite useful to see what's going on here. And that's it for a quick demo. People can play with this. They just have to get a recent copy of licensed Microsoft Excel. I'll speak to that a little bit later. So I'll go back to finish the presentation. I've previously identified 5 climate change industry flaws in their physics and modeling. I'm going to cite this as climate change industry flaw number 6 because of its lack of precision, generating more meritless fear attention when people needlessly worry about the upper end. Even at 5 degrees Celsius, which is 1,050% higher than what the physics calculates, it still isn't their upper end, and it goes on to 6.5 degrees before they call it quits. Yet their lower end goes to 0 before it even reaches 1 Celsius, and the physics computes 0.47 Celsius. Isn't that special? The GHG Lab is hitting the target with a plus minus 10% error and likely a few percent less. So this is a talk that Dr. Happer gave at the European Institute for Climate and Energy. His last slide in his presentation showed his calculation for a doubling of CO2 independent of other gases and a slightly higher 290K instead of 288. He computed a 0.80 Celsius. I've attached the video link to the point in his talk if you wish to see it. His closing comment on his slide is, so I'm willing to bet within 50 years, when the answer is actually known, that it will be a lot closer to this than it is to the IPCC models. Dr. Happer's calculation is confirmed now by GHG Lab at 0.83 for his temperature choice and using GHG Lab's default parameters. I'd now like to revisit the story on Venus with the current understanding about the greenhouse effect that I have. Venus has a 20-kilometer thick cloud layer completely covering the planet. This suggests there can't be a greenhouse effect for radiation coming from the planet's surface as it is trapped in the Venus system. So let's look further into it. This is a flash slide, so I'm just going to briefly talk about it. It cites some NASA data comparing Earth to Venus. The slide also points out an observation that Venus exhibits a characteristic negative slope like Earth, where an increase in altitude causes a decrease in temperature. That effect on Earth is known as the lapse rate, or adiabatic expansion. My hypothesis is that Venus's high surface temperature is from adiabatic compression down to the surface of a dense atmosphere and not any greenhouse effect with CO2. So this is another flash slide. And here you can see, when I did the plot, what the slope looks like. It's very reminiscent of, if you look at some of those lapse rate slopes for Earth. The negative slope plot is shown, and my calculations suggest just adiabatic compression can explain the high surface temperature. The calculation was done from the cloud bottom, which is 50 kilometers high, down to the surface on Venus. The cloud bottom has a pressure of 1 bar, equivalent to Earth's surface atmospheric pressure, and it has a temperature of about 75 Celsius, or equivalent to 348 Kelvin. The surface of Venus has a pressure of 92 bar, which is about 90.7 Earth's atmospheres. A first-order calculation using the adiabatic compression equation that's shown produces a result of 778 Kelvin, which is in the ballpark of Venus's lander-measured surface temperatures around 735 Kelvin. In fact, to further illustrate the point, I decided to substitute nitrogen because it has a higher coefficient for that equation and see what the temperature is. So if you substitute nitrogen which is a non-greenhouse gas, it turns out that Venus's surface temperature and the same pressures, Venus's surface temperature would actually be 430 Celsius higher, or about 1200 Kelvin with nitrogen, a non-greenhouse gas. And on the left, that's the table I used to find the parameters for that equation. This slide also explains that there should be a greenhouse effect on Venus, and it is between the top of the clouds and outer space. Here I've explained how I used the GHG Lab to do the calculation by scaling Venus's situation to input appropriate parameters into GHG Lab to basically fake out GHG Lab to do the calculation. The GHG Lab experiment images are on the next page, but the table on the lower right reveals the result. It is, if my understanding is correct about Venus, it has about 1/3 the greenhouse warming effect as Earth. And if my understanding is correct, I'm citing my 7th climate change industry flaw as stating Venus is an example of a runaway greenhouse effect in the present tense. It is speculated that a runaway greenhouse effect might have occurred in the very distant past, but that isn't an excuse for the inference that is causing a large greenhouse effect today. The non-technical analogy would be referring to a city where crime was once out of control but was cleaned up a long time ago, and referring to that city as an example of runaway crime in the present tense. That would be misleading. And this just shows the result, getting about the 12-degree thing. And then I went deeper into the atmosphere to pick a lower emission point, so there's more of a greenhouse effect, and it didn't change matters much. So that's kind of like a sensitivity test. So I've set up a peer review form for scientists and engineers to review the physics and modeling. It includes 4 boards, one for Earth's physics and modeling comments, one for Venus's physics and modeling comments, and 2 more boards for everyone to use. I'm encouraging participation from both Camp 1 and Camp 2. And just, this is a little helpful slide. It's a flash slide, but this is what I used for doing my greenhouse or my black body calculations for many months before I was coding the equations into Excel. So it's the best one I found, and you can read that if anybody's got a little bit of a science mind and wants to learn a little bit about black body radiation. It's a great website. And then in terms of trying GHG Lab, some people may have a licensed current version or near current version on their machine, but there's a free trial you can get for 30 days. And the other thing about GHG Lab, you have to activate macros, and that's a source of concern for people because that's where some viruses get in. So if you're nervous about that, my suggestion is just to put GHG Lab on an older machine that you don't care about, and put that 30-day trial license on that, and you're good to go. You just won't have it runs without internet access. You just won't have access to our support page and our user documentation, which goes back to the website. And I'm not sure how many in the audience will be trying GHG Lab that don't have Excel, but if a lot of people sign up for Microsoft's trial, they might think whatever company they are using for marketing is working better than before. Okay, the title for this slide is Wolf Wolf, and that's from The Little Boy Who Cried Wolf. So for those who fall for each cry of alarm from climate change zealots, perhaps they've never heard of that story when they were young. There comes a time when even the people who believe them need to see through it and say, wait a minute, you've lost your credibility and I'm no longer listening to you. So I'd like to express some personal perspective on just 3 of the recent Wolf Wolf cries. Much of it can be debunked if people were willing or able to do simple calculations to acquire perspective. The 3 examples I've chosen illustrate that point. So recently I heard someone going on about waste heat and the possibility that in 400 years, it will boil away the oceans. They base this on a prediction that waste heat may go up by a factor of 10 every century. A quick calculation shows that the sun's annual energy on Earth is over 7,000 times the heat from burning a year's worth of fuels we consume. So current waste heat would be under 0.01 Celsius. If the population peaks a century, why would waste heat keep going up at all, let alone be 10,000 times its current value in 400 years? Instead, they should have been worried about past waste heat from urban development during the last 100 years near temperature measuring stations influenced the temperature measurements, as some have pointed out, like Tony Heller. That mistake on its own could easily nullify their equilibrium climate sensitivity. With the IPCC's prediction of a much higher temperature rise from GHGs than supported by physics, Why would a few degrees be a problem at all? This is another one. Plants and animals adapt to wide swings in temperature daily and annually without a problem. And taking the difference between the average equator temperature and that of the North Pole, we learned that for every degree of latitude, it is a 0.7 Celsius change in temperature. So a degree of latitude is only 69 miles. So 3.5 degrees of average temperature change is like a latitude change of 350 miles. Finally, the methane from the permafrost fear is another irrational fear, easily shown with a quick calculation. It is not like an increase in the temperature thaws the entire Arctic, like a freezer door being accidentally left open. The region of the Arctic where the annual zone of freeze-thaw cycles occurs will only shift north 7 miles for every 1/10 of a degree increase. So GHG Lab predicts the warming from GHGs will push that 14 miles north by 2075. So I put my best effort into this R&D and building GHG Lab because I felt it would be a valuable contribution to the efforts others had put into exposing the baseless claims of the climate change industry. I want it to be both educational, but more importantly, produce convincingly accurate results so people would get behind it and share it to critical industries with enthusiasm. The goal was so others will use it and share it with those who would benefit the most. Industries like oil and gas, agriculture, and automotive have been threatened and maligned by establishment climate narratives for years. Increasingly severe climate mandates are now getting pushback, and a tool to refute the bad science could strengthen them and encourage others. Maybe the climate mandates can fall quickly now. So some of your guests, including scientists on your show and in other interviews, take time to express their own concern over the damage that has already been done by climate change narratives and mandates, and if things continue, the damage that will be done to human progress. So I'd like to opine on this and also the mission as I see it in the closing 3 slides. So for audience members that have connections with any of the industries or perhaps just social media, your support by helping make those connections is crucial. And there is strengthened defensive information too. For instance, in the agriculture, as this slide outlines, I provided the centered methane and nitrous oxide projection equations, identified some of the worst climate change industry errors that are easily exposed through GHG Lab, and provided a tool to compute GHG-caused temperature increase, results that now nullify the alarmism over the half-lives of those agriculture GHGs. It is my opinion that any who side with protecting our food supply are now equipped with enough information to defend on the science and refute misguided science. So Carl Sagan got me into this with his assurance in his 1985 Congress talk. So I thought I'd give him the third and last quote of my presentation. I went looking for something that fits with the establishment climate change narrative, and like this one from his book, The Demon-Haunted World, Science as a Candle in the Dark. He says, one of the greatest commands of science is to mistrust arguments from authority. Too many such arguments have proved too painfully wrong. Authorities must prove their contentions like anyone else. So going forward, my objective, I look forward to team up with any individuals, organizations, and industries that seek to halt the direction society is being forced into by the establishment with their climate change narratives. It feels to me like we are in a relay race for the preservation of freedom and human progress. Perhaps this is the final leg of that race. Let's win it for the prize of a long overdue end to authorities' dangerous nonsense. Many have put in a fine effort pursuing the same direction to halt climate change mandates. I hope the R&D I've worked on, including releasing GHG Lab, can be of some help to tip the scales to that end goal very soon. I'll say that again. Many have put in fine efforts pursuing that same direction to halt the climate change mandates. I hope the R&D I've worked on, including releasing GHG Lab, can be of some help to tip the scales to that end goal very soon. So I mentioned earlier that believing can carry the day in religion and sports. I now take the liberty to say, for this relay race, I really believe we can win this working as a team. I'd like to thank the audience for their interest. Perhaps they can play a role in sharing what they've learned in this presentation with people they already know in those essential industries I mentioned. Thank you.
I just wanted to mention that in the show description right now, I have 4 links to your learning center, to downloading the lab software, the link to your peer review forum, and to your Twitter feed. And then also, I will be putting a link to your PDF of your slides, right?
Yeah, I'll send that to you right after this.
And then I just wanted to step back at the big picture and just summarize what you said at the very highest level, that if we double CO2 from here, you're saying we probably can't even double it, given demographic trends. We probably won't double it. Is that right?
That's what I'm saying is you have to look at the half-life. So you get an overshoot, right? Like with your engineering background, you've got what's going to happen right now. It's a slight, if you look at those curves, there's a slight exponential thing. It's not a straight line going up. It just slightly accelerates going up. And what's going to happen is as we hit that knee of the population peak, obviously that acceleration has an inflection point and it starts to flatten and then it starts to come down. The overshoot has to do with half-life, right? So if you had a constant input into a system and you had a half-life, it was a flat line constant input, the half-life's irrelevant. It's only when you're adding more and more that the half-life has this effect. So we're going to hit that point. So I don't know. It's just like their predictions or temperature predictions. If you look at one website, you're going to find half-lives that are dramatically different from some other website. So I couldn't nail down any consensus on half-lives. It was just all over the map, and it varied like by a factor of 10. Right, from one website to another. And they're trying to use half-life as some kind of as I understood it, a potency of the nitrous oxide is 280 times more potent than CO2 over a 100-year period or something. And I just don't get it. Like we're talking about something that when I quadrupled it and quadrupled methane, we got 0.22 degrees, and we're out 300, 400 years on that exponential curve. It's just a bunch of fear mongering, just ridiculous, absolutely ridiculous.
And then if I heard you right, there is a major point that Happer had ECS at about 0.8 and you had it at about the same, correct?
Yeah, 0.83 for the same temperature and with no other gases, no water vapor or anything. When I looked at his slide, that was his calculation. And the interesting thing was, he was saying, I know he does good calculations. Like I've looked at some of his stuff, and the interesting thing was he was thinking 50 years from now we're going to find out what the truth is. And I'm saying, you got the truth right here. Look, there's your confirmation. So I'm very curious when this airs. I'm very curious what he's going to do and what Moncton's going to do, and some of these people that have been fighting the good fight for, like I think. Lord Moncton's like 10 years or more. I saw old videos of him 10 years ago talking about this stuff. So it's going to be very curious as to how engaged they get with this, what they're going to do with it. I might get some, people doing a lot with it. I don't know. Like it's when you put a tool in somebody's hands, it's a lot different than writing a paper. And so I still haven't written that darn essay. I wrote it back in December of 2022, showed it to a few people, including people I didn't personally know, like let's say 5 people, didn't get any feedback on it. And I'd actually concluded based on that step function research papers, got me averaging or using the average coefficient and a step, like a range for a zone. I actually concluded 1A was right. Group 1A was right. And that's why I bought climatebell.org, because oh my God, it's a nothing burger. And so I bought that but then I thought, well, I'm not happy with the way I did my calculations, because I just took that step function. Now I can see the detail in the spectra and I can do more calculations. So that took me to step 2, and I wrote part of another version of the essay. I hate writing essays. So I like coding. I like doing something with my hands. So my friends are bugging me. You've got to write that essay now. And I've got version 3 partially done. And then I've circulated to a few friends, and one goes, "Where's your peer-reviewed papers? You're not referencing enough peer review." And I don't have institutional access. So all I get is what squirts out on the web, a draft paper or something. Sometimes I get the real thing. And I basically I'm starved of information, but I still have a lot of information at my fingertips. But it's not like the good old days when I was at university and you could go down to the library and browse through. I suppose I could drive to Ottawa U or something and sneak my way in. I don't know what the security is like for someone coming in off the street, but I don't want to drive back. Like the problem with doing research is you need access at your fingertips. If I drove down to the university, I'd waste 2 hours and spend money on parking and maybe find an answer to my question. I come home and generate another question, and then I have to drive back again. So it's really difficult unless you have electronic access to these journals. So, and I'm not too impressed with peer-reviewed journals. I think I've heard some of your guests talk about the problems of corruption and so on. And I even had in my day the only time I ever used peer-reviewed journals, except for this personal assignment, was when I did my graduate work at U of T in 82 to 85. And I collected over 100, I think it was 106 papers on my research topic, which was CMOS latch-up, the semiconductor parasitic SCR in the MOSFET technology. It had to be solved. And the industry was trying to solve it with rapid simulations using SPICE. And it was actually solved a few years later by some smart guys in processing that put trenches into the chip. So they basically cut the virtual wires of the feedback loop and solved the problem that way, which is the correct way to solve it. Like, we wouldn't have chips of 10 billion transistors today if it wasn't solved. Like, it was already a problem back in the 80s. So it actually got solved by processing, which is the right way to do it. But anyway, the point of those papers, I found many dozens of them did their measurements wrong and missed the zone of modeling that was important to actually do the modeling. And there was no corruption back then in this. This was industries working together to try to solve a problem, a real industrial problem. So there was no politics in it. And so there's nothing to be sinister. It was just bad peer reviewers and parroting. In my opinion, the only explanation for this fundamental mistake was some guy measured it and some other guy goes and measures it the same way. And it was just a sequence of parroting the same bad lab experiment. The modeling was one thing, but their measurement technique, they missed it. I can explain. It's pretty simple, but I was shocked. Only 4 papers out of the 100 and some had it right. So I actually not 97%. I have a 96% proof that 96% of the scientists can measure something wrong. Anyway, it was so when I put this thing out there for peer reviewed thing, I'm not too keen on it, but if a bunch of people want to do it, then maybe the only reason I would do it is because it'd be interesting to test the peer review thing with researchers that have been published in those journals, and now they get rejected. A whole herd of good researchers get rejected because we're not singing this from the choir book, right? So that would be my interest in seeing what happens.
Any final point you'd like to make before we finish this one up?
No, I'm just curious as to what's going to happen. I mean, I spent 2 years of this, and my wife was saying I need to go out and bring some money in because we're not in a bad situation or anything. But every month I get reminded. Have you? Because I had some contract work that was bringing in some money, not big money. It was a friend's startup company. It wasn't well financed, so I was doing that when COVID struck, and we were 1 week away from going to our national trade show. So I was helping them out on a bunch of different things, and it got canceled for COVID. So that was a big missed opportunity for the company, and the company went under about 2 years later. Not just because of that, but if we'd had that trade show that we'd booked and everything, it would have possibly given us a lot of good face-to-face time with the clients. It was a big show, and we're very disappointed that we didn't have that. So I got a little bit of an axe to grind with COVID.
All right. Okay. I will let you go. Rodney McInnis, thank you very much. And I'm excited to put this up online and see what people say. Thank you very much.
Thank you very much.
Right, talk to you later. Bye.
Yeah, bye.